Good evening and welcome to Dreamy Academy. Tonight we begin a quiet journey into the very foundations of existence, exploring the silent architecture of the cosmos. As we begin, I'd love to know where you're watching from, your city, your country, perhaps even what the night sky looks like outside your window. If you enjoy these peaceful explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of quiet curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and thoughtful adventure. Tonight, we begin with a beautiful paradox. The universe, in all its vastness and complexity, is built almost entirely of nothing. Right now, as you listen, your hand rests on a surface that feels utterly solid. Your body, your chair, the air around you, all seem substantial, unwavering. Yet, at a scale too small for our eyes to perceive, every single thing you encounter is a shimmering, almost entirely empty expanse. It is a dance of forces in a vacuum, a tapestry woven from threads of pure energy and probability. This fundamental emptiness, this deep truth about the nature of matter, is not a lack, but an astonishing elegance. It's the secret language of creation, the quiet hum that underpins everything from the smallest subatomic particle to the grandest galaxy. To truly appreciate the universe, we must first learn to see through the illusion of solidity, to understand the profound beauty in what isn't there, and to marvel at the forces that conjure substance from almost pure space. This is a story of wonder, not as a fleeting gasp, but as a deep, abiding hum that lulls the mind into a state of peaceful understanding. Let us begin by gently lifting the veil on the very essence of matter. Have you ever considered what it means for something to be truly solid? Your hand resting in your lap feels like an undeniable presence. The floor beneath your feet supports your weight with unwavering certainty. Yet the universe has a quiet secret it whispers only to those who look closely enough. Everything you perceive as solid is, in fact, mostly empty space. Let's begin by considering the ordinary miracle of an atom. For centuries we imagined these fundamental building blocks as tiny, hard spheres like miniature billiard balls. But the truth, revealed by patient experimentation and profound thought, is far more subtle and far more beautiful. Picture, if you will, the atom as a vast empty cathedral. In the very centre, almost unimaginably small, sits the nucleus, a dense, positively charged core containing protons and neutrons. If this nucleus were the size of a tiny fly buzzing in the centre of that cathedral, the outer edges of the atom, defined by the swirling presence of electrons, would be the very walls of the building itself. The space between the fly and the walls, utterly, beautifully empty. This isn't just a poetic analogy, it's a precise description. The nucleus accounts for 99.9% of the atom's mass, but only about 0.001% of its volume. The atom is essentially empty space with a dense core and a fuzzy cloud of probability. And those electrons, which define the atom's outer boundary, don't orbit like planets around a sun as we once imagined. That picture, though useful for a time, isn't quite right. Instead, electrons exist in probability clouds, regions where they are likely to be found, defined by the intricate rules of quantum mechanics. They are less like tiny balls and more like a pervasive hum, a wave of potential, existing in multiple places at once until observed. This means that the solidity of matter, the very thing that prevents your hand from passing through the table, is not due to physical contact in the way we usually think of it. It's a consequence of these electron clouds, and the forces they exert. If atoms are so empty and electrons are merely probability clouds, what then holds anything together? Why don't all the protons in a nucleus, with their identical positive charges, simply repel each other and fly apart? And what keeps those elusive electrons tied to the nucleus, rather than drifting off into the void? The answer lies in the elegant interplay of the universe's fundamental forces, a quiet, constant ballet that shapes everything from the smallest particle to the grandest galaxy. At the heart of the atom, within that tiny, dense nucleus, an incredibly powerful force is at work, the strong nuclear force. This is the universe's most potent binding agent, so strong that it utterly overwhelms the electromagnetic repulsion between positively charged protons. It's a force with an astonishingly short reach, operating only across distances smaller than the nucleus itself. Imagine it as a tiny, incredibly tenacious glue that snaps into action only when particles are almost touching, binding protons and neutrons together with an intensity that is almost beyond comprehension. Without this force, no atomic nuclei heavier than a single proton hydrogen could exist. No carbon, no oxygen, no iron. None of the elements that make up our world, our bodies, or the stars themselves. The strong force is the silent architect of atomic identity. Beyond the nucleus, holding the electrons in their probabilistic dance around the core, is the electromagnetic force. This is the force we experience most directly in our daily lives. It's responsible for light, for electricity, for magnetism, and crucially for all of chemistry. It's the electromagnetic force that causes electrons to be attracted to the positively charged nucleus, keeping them within the atom's fuzzy boundaries. And it's the electromagnetic force between the electron clouds of different atoms that prevents them from passing through each other. When you press your hand against a table, you're not feeling atoms touching in a solid sense. You're feeling the electromagnetic repulsion between the electron clouds of your hand and the electron clouds of the table. This force, while weaker than the strong nuclear force, has an infinite range, shaping interactions across vast distances, even though its effects diminish rapidly with separation. It is the sculptor of molecular forms, the weaver of the chemical tapestries that make up planets and people. There are two other fundamental forces, of course. The or weak nuclear force governs certain types of radioactive decay, transforming one kind of subatomic particle into another, a crucial process in stellar evolution, but one that largely operates unseen in our everyday experience. And then there is gravity, the familiar pull that keeps our feet on the ground and the Earth orbiting the Sun. At the scale of atoms, however, gravity is almost laughably weak, utterly dwarfed by the electromagnetic and strong nuclear forces. A tiny magnet can lift a paperclip, overcoming the gravitational pull of the entire Earth. Yet, over cosmic distances, where masses become immense and other forces cancel out, gravity reigns supreme, shaping galaxies and dictating the lives of stars. So the seemingly solid world around us is, in fact, a delicate balance of these fundamental forces acting within mostly empty space. Your body, the air you breathe, the ground beneath you, all are intricate patterns of subatomic particles held in precise, energetic arrangements by these unseen hands. The solidity you perceive is an emergent property, a grand illusion created by the electromagnetic repulsion of electron clouds. It's a testament to the elegance and efficiency of the universe's design that such a rich and varied reality can emerge from so much emptiness, bound by such fundamental rules. There is a particular comfort in understanding this. It tells us that the universe, though vast, is also intimate, made of the same patterns repeated at every scale. What we perceive as distinct objects are merely different arrangements of these fundamental particles and the forces that orchestrate their dance. This knowledge changes perception. It reveals the profound beauty in the mechanism itself. The universe isn't a collection of separate things, but a continuous, interwoven tapestry of energy and interaction. This profound emptiness within matter, sustained by the invisible ballet of fundamental forces, is the starting point for understanding everything else in astrophysics. If atoms are the fundamental building blocks, then the next question that arises naturally is how these empty, force-bound structures combine to create the astonishing diversity we see around us. How do these individual atoms interact and arrange themselves to form molecules, dust, gas, planets, and eventually the fiery hearts of stars and the intricate spirals of galaxies? How does the subtle language of forces lead to the complex chemistry that governs all life? That question leads us into the world of light and interaction, into the very ways atoms communicate across the vastness of space, building the universe one elegant connection at a time. Welcome back, seekers of quiet understanding, to our shared journey through the cosmos. We left off last time pondering a profound paradox. How does a universe built from mostly empty atoms, held together by invisible forces, give rise to the rich tapestry of matter we perceive as solid and real? How do these ethereal building blocks combine to form molecules, planets, stars, galaxies, and even the intricate dance of life itself? The answer, like so much in the universe, lies in a delicate balance of forces, a nuanced conversation between the almost nothingness of atoms. If the strong nuclear force is the steadfast heart of the atom, holding the nucleus together, and gravity the silent architect of cosmic structures, then the electromagnetic force is the tireless weaver, spinning the threads that bind atoms into molecules. It orchestrates the intricate ballet of electrons, those elusive wisps of probability that define an atom's outer boundaries. Imagine, if you will, the electron clouds we spoke of, not as solid shells, but as fuzzy, undulating fields of negative charge, unique to each element. These clouds are where the magic of atomic interaction truly happens. Atoms, in their fundamental nature, seek stability. They yearn for a complete outer electron shell, a state of cosmic contentment that minimizes their energy. The noble gases, like neon and argon, already possess this perfect arrangement, making them aloof, uninterested in forming bonds. But most other elements are not so fortunate. Their outer shells are incomplete, leaving them with an innate drive to either gain, lose, or share electrons. This drive is the engine of chemistry, the fundamental impulse that transforms individual atoms into the complex structures of molecules. It's a dance of attraction and repulsion, a subtle negotiation mediated by the electromagnetic force. When two atoms approach each other, their electron clouds might initially repel, as like charges do. But if the conditions are right, if their energetic needs align, they can find a way to interact. Consider the act of bonding. It's not a collision of solid objects, but a merging or sharing of these probability clouds. In a covalent bond, atoms gracefully share electrons, allowing their outer shells to overlap and effectively achieve that coveted state of stability together. Think of it as two individuals, each with an incomplete puzzle, deciding to combine their pieces to complete a larger shared picture. The electrons are no longer solely associated with one nucleus, but are now shared between them, forming a strong invisible bridge. This shared electron density creates a powerful attraction, holding the atoms together in a specific geometric arrangement. In a ionic bond, the exchange is more dramatic. One atom with a loosely held electron might generously donate it to another atom that has a strong affinity for acquiring one. The donor atom becomes positively charged, a cation, having lost a negative electron, while the acceptor atom becomes negatively charged, an anion. Now these oppositely charged ions, drawn together by the unwavering electromagnetic force, form a bond. It's an electrostatic embrace, a powerful attraction between positive and negative, creating a stable new entity. Thus, from these elegant negotiations, molecules are born. A simple water molecule, H2O, is not three separate atoms loosely associated, but a precisely angled structure, two hydrogen atoms covalently bonded to a single oxygen atom. The very essence of its properties, its ability to dissolve substances, its unique density changes with temperature, its role as the solvent of life, emerges from this specific arrangement of shared electrons and the geometry it dictates. And yet even a molecule of water, or a complex protein, or the crystalline lattice of a diamond, remains fundamentally a vast expanse of empty space. The apparent solidity of a molecule, just like an atom, is an emergent property, a symphony of electromagnetic repulsions and attractions that prevent the nuclei from ever truly touching, while the electrons buzz around, defining its open interactions. It is a testament to the astonishing elegance of these fundamental forces that such intricate, stable and diverse structures can arise from so much nothingness. But how do we, observers on a distant planet, come to understand these invisible dances and silent negotiations? How do we peer into the hearts of stars or discern the composition of nebula billions of light years away? The answer lies in the universe's most eloquent messenger, its universal language, light. Light, as we perceive it, is merely a sieve of the vast electromagnetic spectrum. It is a form of energy that travels through the vacuum of space at an astonishing speed, carrying with it a wealth of information. At its heart, light is both a wave rippling through the fabric of space-time and a particle, a discrete packet of energy we call a photon. These photons are the currency of atomic communication, the postcards exchanged between the smallest constituents of matter across the cosmic expanse. Imagine an atom peacefully existing in its stable state. Its electrons occupy specific energy levels, like steps on a ladder. Now, introduce a burst of energy, perhaps from a collision with another atom or a nearby source of heat. This energy can excite an electron, causing it to momentarily jump to a higher energy level, to a higher step on that ladder. This state is unstable, fleeting. The electron, yearning for its original lower energy state, quickly falls back down, and as it descends, it releases the excess energy it absorbed, not as heat, but as a photon of light. Crucially, the energy of this emitted photon is precisely equal to the difference between the two energy levels the electron jumped between. Because each element has a unique set of electron energy levels, a distinct ladder of steps, each element emits a unique set of photons, a distinct pattern of colors or wavelengths. It's like each element has its own distinct signature tune, its own specific set of musical notes it can play. This is what we call an emission spectrum. Conversely, atoms can also absorb light. If a photon with precisely the right amount of energy, matching the energy difference between two electron levels, strikes an atom, that photon will be absorbed and the electron will jump to the higher level. Photons of other energies will simply pass through. This means that if you shine a continuous spectrum of light, like white light containing all colors, through a gas of atoms, those atoms will absorb only their specific signature wavelengths, leaving dark lines in the otherwise continuous spectrum. This is an air absorption spectrum. These unique patterns, these spectral fingerprints, are the keys to unlocking the universe's secrets. They are the cosmic barcodes that allow us to identify elements present in distant stars, nebulae, and even the atmospheres of exoplanets, without ever having to touch them. This incredible technique is called spectroscopy. When we point our telescopes at a distant star or galaxy, we are not just seeing a point of light, we are intercepting billions upon billions of these atomic postcards, each carrying information encoded in its wavelength. By splitting the incoming light into its constituent colours, much like a prism does, we reveal these hidden messages. What wonders do these spectral lines tell us? Composition. The presence of specific emission or absorption lines immediately tells us which elements are present. We can identify hydrogen, helium, carbon, oxygen, iron, and countless other elements in the most distant reaches of the universe. This is how we know that the universe, from the smallest atom to the largest galaxy, is built from the same fundamental ingredients. Temperature. The intensity and breadth of these spectral lines, as well as the overall distribution of light across the spectrum, reveal the temperature of the emitting or absorbing gas. Hotter objects emit more energetic photons and glow bluer, while cooler objects emit less energetic photons and glow redder. Motion, perhaps one of the most profound revelations from spectroscopy, is the ability to determine how celestial objects are moving relative to us. This is due to the Doppler effect. If a light-emitting object is moving away from us, its light waves are stretched, shifting its spectral lines towards the red end of the spectrum. Redshift. If it's moving towards us, its light waves are compressed, shifting its lines towards the blue end. Blue shift. This phenomenon allowed Edwin Hubble to discover that the universe is expanding, with most galaxies receding from us, their light profoundly redshifted. Density and pressure. Even the width and sharpness of spectral lines can tell us about the density and pressure of the gas, as these conditions affect how frequently atoms collide and interact, subtly altering their emitted light. Take a moment to truly appreciate this. From the quiet confines of our planet, we are reading the autobiographies of stars that lived and died billions of years ago. We are discerning the chemical recipes of planets forming in faraway stellar nurseries. We are tracing the expansion of the universe itself, all by interpreting the subtle shifts and patterns in the light that has travelled across unimaginable cosmic distances to reach our instruments. This understanding of light as a carrier of atomic information is not merely a fascinating detail, it is the absolute cornerstone of modern astrophysics. Without it, our knowledge of the universe beyond our solar system would be almost non-existent. It is the bridge between the quantum realm of electrons dancing in their probability clouds and the grand, majestic scale of galaxies colliding and stars being born. It is the invisible thread that connects the fundamental forces governing an atom to the cosmic forces shaping the largest structures in existence. In this universe of vast emptiness, where solidity is an illusion and matter is a fleeting arrangement of forces, light emerges as the constant, reliable messenger. It turns the silent architecture of the cosmos into a vibrant, communicative entity, inviting us to listen, to observe, and to understand. We are not merely observers, we are interpreters of this ancient, ongoing conversation, piecing together the story of everything from the whispers of individual atoms to the resounding symphony of the expanding universe. As we continue our slow and thoughtful adventure, we will carry this profound understanding of light with us, It will be our guide as we next delve into the birth and death of stars, the formation of planets, and the grand cosmic narrative that unfolds across billions of years and unimaginable distances. For it is through light that the universe reveals itself, and through light that we, the curious inhabitants of a small blue planet, can begin to comprehend our place within its astonishing, elegant design. We spoke of light, the universe's tireless messenger, carrying tales from the deepest reaches of space. We learned how its photons, imbued with the unique fingerprints of atoms, allow us to peer into the very composition and motion of distant celestial bodies. But what stories do these photons whisper about the very beginning, about the origin of the matter they illuminate? And how, from the vast emptiness we discussed, do these fundamental particles and forces coalesce into the dazzling beacons we call stars? Your gaze perhaps drifts outside your window to the seemingly solid world around you. We've discovered that this solidity is an illusion, a dance of forces across immense atomic voids. Now let us gently lift the veil on an even more profound paradox. The universe, which is now so profoundly empty, began in a state of unimaginable density and energy. Imagine, if you will, not the tranquil star-dusted night sky, but a cosmos in its infancy, a universe not yet vast and cool, but impossibly compact, searingly hot, a crucible of pure energy. This was the moment of the Big Bang, not an explosion into space, but the rapid expansion of space itself, bringing with it the very fabric of time and matter. In those first fleeting moments, the universe was too hot, too energetic for even the simplest atoms to exist. There were no electrons orbiting nuclei, for there were no stable nuclei to orbit. Instead, a primordial soup of fundamental particles, quarks, leptons, and the force-carrying bosons, danced in a chaotic, fiery ballet. As the cosmos expanded, it cooled. This cooling was the universe's first great act of creation. With each drop in temperature, the conditions became just right for new transformations. Within minutes, not billions of years, but mere minutes after the initial expansion, the universe had cooled sufficiently for protons and neutrons to form and, crucially, to begin to fuse. This epoch, known as Big Bang nucleosynthesis, was the universe's initial forging. Under immense pressure and still intense heat, a proton and a neutron could bind, forming deuterium, a heavy isotope of hydrogen. Add another proton, and you have helium-3. Add 2 neutrons and 2 protons, and you have helium-4, a stable, light nucleus. This was a profoundly significant event, for it determined the initial composition of the universe. For every 12 hydrogen nuclei single protons formed, approximately 1 helium nucleus, 2 protons, 2 neutrons, was created, along with trace amounts of lithium. These were the universe's first architects, the simplest building blocks forged in a cosmic furnace that has since dimmed. And the abundance ratios we observe today, roughly 75% hydrogen, 25% helium by mass, are a powerful confirmation of this early cosmic drama, a direct echo from the dawn of time, recorded in the very elements that comprise everything around us. Yet even with this initial scattering of hydrogen and helium across a rapidly expanding canvas, a silent, patient force was at play: gravity. In the grand cosmic scheme, gravity, which we noted was negligible at the atomic scale, reigned supreme. It is the sculptor of galaxies, the orchestrator of stellar births, the silent architect of the cosmos. Despite the universe's headlong expansion, there were always minute variations in the density of this primordial gas, regions where the hydrogen and helium were slightly more concentrated than others, and gravity, with its inexorable pull, began to take notice. Slowly, imperceptibly at first, these wisps of hydrogen and helium began to gather. Over millions of years, what began as subtle ripples in the cosmic fabric grew into colossal clouds of gas and dust, vast nebulae spanning light years. Within these colossal nurseries, denser pockets emerged, tiny gravitational eddies pulling in more and more gas from their surroundings. Imagine a gentle whirlpool forming in a vast, calm ocean, slowly drawing in everything around it, gaining momentum and substance. This is the nascent stage of a star. As these pockets of gas grew, their gravitational pull intensified, drawing in even more matter. The cloud began to contract, spinning slowly at first, then faster as it shrank, conserving its angular momentum, much like a skater pulling their arms in to spin faster. This slow, majestic collapse, driven by gravity, caused the core of the condensing cloud to become hotter and denser. Particles, once free to roam, were increasingly squeezed together, their random motions translating into a rise in temperature. This is a protostar, a star in its infancy, still gathering mass, still warming, but not yet truly alive. It glows, but its light comes from the heat generated by its gravitational collapse, not from nuclear fire. The journey from a diffuse cloud to a glowing protostar can take millions of years, a testament to the patient, unhurried nature of cosmic evolution. But eventually a critical threshold is crossed. As the protostar continues to contract, the temperature and pressure in its core climb to unimaginable levels, tens of millions of degrees Celsius, pressures millions of times greater than anything on Earth. And then something extraordinary begins. This is the moment of stellar birth, the ignition of nuclear fusion. No longer is it merely gravitational collapse. It is a deep alchemical transformation. Under these extreme conditions, the hydrogen nuclei, the single protons that comprise the vast majority of the star's mass, are forced together with such immense energy that they overcome their natural electromagnetic repulsion. They fuse. In a process primarily known as the proton-proton chain for stars like our Sun, 4 hydrogen nuclei combine to form a single helium nucleus. This transformation is not just a rearrangement of particles, it is a profound conversion of mass into energy. As Albert Einstein so elegantly revealed with his famous equation EmC2, a tiny fraction of the mass of the original hydrogen nuclei is converted into an enormous burst of energy. This energy, released in the form of gamma-ray photons, streams outwards from the core, pushing against the inward crush of gravity. This is the engine of a star, the source of its relentless, glorious light, the very reason it shines. A stable star like our Sun is a magnificent ongoing battleground where 2 titanic forces are perfectly balanced. The crushing inward embrace of gravity, forever trying to collapse the star, is precisely counteracted by the immense outward pressure generated by the nuclear fusion raging in its core. This equilibrium, known as hydrostatic equilibrium, is what defines a main sequence star, allowing it to shine steadily for billions of years, a cosmic beacon of light and life. And what does this tell us about the light we receive? Everything. The light that travels across the vastness of space to reach our telescopes bears the indelible imprint of these stellar processes. Recall our discussions of spectroscopy, the art of deciphering light's hidden messages. Now we apply this to the stars themselves. The colour of a star, as you might observe, is a direct indicator of its surface temperature. Hotter stars, burning fiercely, emit more blue and ultraviolet light, appearing dazzling white or blue-white. Cooler stars with less energetic surface temperatures glow with the warmer, redder hue. This simple observation led astronomers to classify stars by their spectral types, a sequence that runs from the hottest and bluest to the coolest and reddest. O, B, A, F, G, K, M. Our own Sun, a comfortable yellow, is a G-type star. Each of these spectral types corresponds to a distinct set of absorption lines in the star's spectrum. The specific elements that absorb light and the intensity of those absorption lines depend critically on the star's surface temperature and pressure. For instance, very hot O-type stars ionize much of their hydrogen, so their spectra show weaker hydrogen lines but strong lines from ionized helium. Cooler M-type stars, on the other hand, are cool enough for molecules to form in their atmospheres, leading to complex molecular absorption bands. By meticulously analyzing these stellar spectra, we can do more than just determine composition and temperature. We can infer a star's mass, its luminosity, and even its evolutionary stage. The Hertzsprung-Russell HR diagram, a foundational tool in astrophysics, plots a star's luminosity against its surface temperature, or spectral type. On this diagram, stars fall into distinct groups, revealing patterns, family trees of stars guiding us through their lives from birth to eventual demise. The vast majority of stars, including our Sun, reside on the main sequence, a diagonal band stretching from hot, luminous blue giants to cool, dim, red dwarfs, all powered by the steady fusion of hydrogen into helium. Thus, the light that began its journey from the scorching core of a newborn star, slowly migrating outwards, bouncing and scattering through its dense interior, eventually escaping into the vacuum of space, carries with it the entire story of its creation and its ongoing fiery existence. It is a testament to gravity's patient work, to the universe's initial conditions, and to the extraordinary power of nuclear alchemy. With each photon, we are not just observing a distant point of light, but reading a chapter in the grand saga of cosmic creation, understanding how the universe transformed from an empty void into a tapestry woven from the glory of a billion suns. And this is just the beginning of their stories, and ours. We have traced the genesis of stars, witnessed the quiet ignition of their nuclear furnaces, and understood how the steady burn of hydrogen into helium sustains them for billions of years. This delicate equilibrium, a cosmic dance between the inward pull of gravity and the outward push of fusion, defines the main sequence phase, a period of serene stability. Yet even the most profound stability is but a chapter in a much grander story. The fuel within these stellar hearts is finite, and as the hydrogen reserves dwindle, the star must embark on its next evolutionary journey, a path dictated by its initial mass, leading to a spectrum of spectacular fates. Take a moment, if you will, to consider the quiet inevitability of change. Just as a candle eventually consumes its wax, a star too will exhaust its primary fuel. For stars like our own Sun, those of low to intermediate mass, this transition is a gradual, majestic transformation. As the hydrogen in the core is depleted, fusion ceases in that central region. The core, no longer supported by the outward pressure of fusion, begins to contract under the relentless grip of its own gravity. This contraction heats the core intensely, and this heat in turn radiates outward, igniting a shell of fresh hydrogen fusion around the now inert helium core. Imagine a fire that has burned down to embers at its center, but whose radiant heat causes the surrounding kindling to flare anew. This shell fusion is often more energetic than the original core fusion. The increased energy output pushes the star's outer layers outward, causing them to expand dramatically and cool. The star swells into a colossal luminous sphere, its surface temperature dropping, causing it to glow with a deep ruddy hue. We call this phase a red giant. You might gaze at the constellation Orion tonight and marvel at Betelgeuse, a nearby red giant, its crimson light a testament to this very process, a star nearing the end of its main sequence life. Within the contracting core of our Sun-like star, the helium atoms grow denser and hotter. Eventually, if the star is massive enough, the temperature and pressure in this helium core reach an astonishing threshold, approximately 100 million Kelvin. At this point, helium nuclei begin to fuse together, forming carbon and oxygen in a process known as the Tsar triple alpha process. For lower mass stars, this ignition can be sudden and explosive, a helium flash, though the star's immense size mutes its outward appearance. For slightly more massive stars, the helium ignites more gently. Once helium fusion begins in the core, the star achieves a new, albeit shorter-lived stability, often shrinking slightly and becoming hotter and brighter, inhabiting what we call the horizontal branch or red clump on the stellar evolutionary diagram. This too is a temporary reprieve. The helium in the core will eventually be exhausted, leaving behind a core of inert carbon and oxygen. The star then enters a second red giant phase, even larger and more luminous than the first, fueled by two shells of fusion, an inner shell of helium burning into carbon and an outer shell of hydrogen burning into helium. This is the asymptotic giant branch, AGB, phase, a period of intense internal activity and instability. The star pulsates, its outer layers becoming increasingly loosely bound. The forces at play are truly profound. The star's luminosity becomes so immense that the outward pressure of light itself begins to push against the star's tenuous outer envelopes. Gently yet inexorably, these outer layers are expelled into space, forming vast, beautiful shells of glowing gas around the exposed hot core. These ethereal structures, often symmetric and breathtakingly intricate, are known as planetary nebulae. Despite their name, they have absolutely nothing to do with planets. The term arose from their planet-like appearance through early telescopes. They are cosmic farewells, glowing testament to a star's passing, enriching the interstellar medium with the carbon and oxygen forged within its heart. What remains? At the centre of these expanding gaseous shrouds lies the stellar ember, the dense, hot core of carbon and oxygen. No longer capable of fusion, it is supported against further gravitational collapse by a quantum mechanical phenomenon known as electron degeneracy pressure. The electrons, packed incredibly tightly, resist further compression, creating a state of matter unlike anything we typically encounter on Earth. This compact, incredibly dense remnant, often about the size of Earth but containing the mass of the Sun, is a white dwarf. It slowly, over trillions of years, radiates away its residual heat, gradually fading into a cold, dark cinder, a black dwarf. Though the universe is not old enough for any black dwarfs to have formed yet, our Sun, in its distant future, will follow this very path. But what of the truly massive stars, those titans born with many times the mass of our Sun? Their lives are accelerated, their stories unfolding with a breathtaking intensity and a far more dramatic finale. Their immense gravity dictates a faster, hotter burn. They race through their hydrogen fuel in mere millions of years, not billions. When their core hydrogen is exhausted, they too swell into red supergiants, far larger and more luminous than their low-mass counterparts. However, their greater mass allows them to overcome the electron degeneracy pressure that halts the collapse in smaller stars. Their cores continue to contract and heat, reaching temperatures and pressures sufficient to ignite fusion of heavier elements. Helium fuses into carbon and oxygen. Then carbon fuses into neon and magnesium. Oxygen fuses into silicon. Each successive fusion stage requires higher temperatures and pressures, and each stage yields less energy and lasts for a shorter period. It's like a cosmic hourglass, each grain of sand falling faster than the last. Imagine the star as an onion, with concentric shells of different elements fusing. Hydrogen in the outermost shell, then helium, then carbon, oxygen, neon, magnesium, and finally silicon in the innermost shell, which fuses into iron. This layering creates a truly astonishing structure, a cosmic factory churning out the elements that will one day form planets and life. But then the star reaches an insurmountable barrier. Iron. Iron is the most stable atomic nucleus. Fusing iron into heavier elements does not release energy. It consumes energy. It's a thermodynamic dead end. Once the core of a massive star becomes saturated with iron, the jig is up. There is no more fuel to burn, no more outward pressure from fusion to counteract the crushing weight of gravity. The fragile balance is shattered. With no energy generation to support it, the iron core collapses with terrifying speed, imploding in a fraction of a second. The outer layers of the star, still undergoing fusion, rush inward, slamming into the now incredibly dense, unyielding core. The core itself collapses past the point of electron degeneracy pressure, crushing electrons into protons to form neutrons. This creates a hyperdense ball of neutrons, barely 20 kilometers across, but with a mass greater than our Sun. The infalling stellar material rebounds off this neutron core, creating a colossal shockwave that rips through the star's outer layers. What follows is an event of unimaginable power and brilliance, a Type II supernova. For a brief, glorious period, the exploding star outshines an entire galaxy, releasing more energy in seconds than the Sun will emit in its entire 10 billion year lifetime. This cataclysmic explosion is not just a destructive force. It is the universe's ultimate forge. The extreme temperatures and pressures generated during the supernova explosion are sufficient to create elements heavier than iron, all the way up to gold, silver, uranium and beyond, through processes known as rapid neutron capture, the R process. These precious elements, vital for the richness and complexity of the cosmos, are scattered across the vast emptiness of space. The legacy of such a titanic explosion depends on the mass of the remnant core. If the core left behind after the supernova is between about 1.4 and 3 times the mass of our Sun, it continues to collapse until it is supported by neutron degeneracy pressure. This creates a neutron store, an object of mind-boggling density. A single teaspoon of neutron star material would weigh billions of tons. Many neutron stars are observed as pulsars, rapidly spinning beacons that sweep beams of radio waves across the cosmos like a lighthouse, a testament to their incredible rotational speeds and powerful magnetic fields. But if the initial star was truly colossal, perhaps 20 or 30 times the mass of our Sun or more, then even neutron degeneracy pressure cannot halt the gravitational collapse. Gravity's victory is absolute. The core collapses without limit, shrinking to an infinitesimal point of infinite density, known as a singularity. This creates a black hole, an object whose gravitational pull is so immense that nothing, not even light, can escape its grasp once it crosses a boundary called the event horizon. Black holes are not cosmic vacuum cleaners, indiscriminately sucking up everything. Rather, they are regions where space-time itself is so profoundly warped that all paths lead inward. We observe them by the effects of their immense gravity on surrounding matter and light, such as the swirling accretion disks of gas that heat up and emit X-rays as they spiral into the abyss. These stellar deaths, whether the gentle exhalation of a planetary nebula or the violent roar of a supernova, are not merely endings, they are profound, necessary beginnings. The material ejected from these dying stars, the carbon and oxygen from red giants, the heavier elements forged in supernovae, enriches the vast interstellar medium. This cosmic dust and gas, infused with the very building blocks of complexity, then becomes the raw material for new generations of stars and, crucially, new planetary systems. We observe these processes through the same fundamental tool, light. The unique spectra of planetary nebulae tell us their composition and expansion rates. The light curves of supernovae reveal their immense energy and the elements they create. The X-rays from accretion disks around black holes betray their unseen presence. Spectroscopy, our window into the universe, allows us to trace the cosmic cycle of birth, death, and rebirth across unimaginable distances and timescales. Consider this then. Every atom of carbon in your body, every atom of oxygen you breathe, every speck of iron in your blood, every trace of gold in your jewelry, all of these elements, save for the primordial hydrogen and helium, were forged in the hearts of long-dead stars or in the cataclysmic moments of their demise. We are, quite literally, stardust. Your very existence is a testament to the grand, ongoing saga of stellar evolution, a continuous process of cosmic recycling that links the earliest moments of the universe to the vibrant life around you. The universe doesn't just create, it recycles, transforming the remnants of one generation into the seeds of the next, an astonishingly elegant and efficient system of renewal. This understanding connects the silent architecture of the cosmos to the beating heart within your own chest, making the universe not a distant spectacle, but an intimate part of your own story. We have journeyed through the violent, glorious deaths of stars, witnessing the cosmic alchemy that forges the elements of our very being. Your hand, if you trace its contours, is a map of ancient stellar explosions, a testament to the universe's most dramatic recycling program. The iron in your blood, the calcium in your bones, the oxygen you breathe, each atom was once locked within the heart of a star, released only through the cataclysmic collapse of a supernova or the gentle exhale of a planetary nebula. How we turn our gaze from the grand finale of stellar lives to the quiet, patient genesis of worlds. Where do these scattered atoms go? How do these newly forged heavy elements, floating in the vastness of space, coalesce into the intricate, vibrant tapestry we call a planet? Imagine, if you will, the remnants of a supernova, a colossal expanding shell of gas and dust, rich with carbon, oxygen, silicon, iron, and all the elements heavier than helium. Or picture the exquisite luminous shroud of a planetary nebula, slowly dissipating, releasing its enriched material into the interstellar medium. These are not merely waste products. They are the fertile soil of the cosmos, the raw ingredients for the next generation of stars and, crucially, for the worlds that will orbit them. Over eons, these diffuse clouds of gas and dust, spread thinly across light years, begin their slow, inexorable dance. Gravity, that persistent sculptor, draws them together. We have seen how it forms stars. Now we observe its more delicate, nuanced work. As these individual atoms and molecules drift through space, they encounter others, forming denser pockets within the larger cloud. These pockets grow, pulling in more material until vast molecular clouds, cold, dark, and immense, form. Within these clouds, often triggered by the shockwaves of a nearby supernova or the passage through a spiral arm of a galaxy, smaller regions begin to collapse. This gravitational collapse is the prelude to creation. As a region of the molecular cloud contracts, it gains angular momentum, much like a spinning ice skater drawing in their arms. This rotation flattens the collapsing cloud into a disk, a vast, swirling platter of gas and dust, hundreds of astronomical units across, with a nascent protostar forming at its very centre. This, dear friends, is a protoplanetary disk, the nursery of worlds. Take a moment to truly envision this. You're not just observing a static image, you are peering into a dynamic, chaotic, yet ultimately orderly process. The material within this disk is not uniform. Close to the fiery heart of the protostar, temperatures are scorching. Here, only the most refractory materials, silicates, metals like iron and nickel, can condense from gas into solid grains. Further out, in the cooler, darker reaches of the disk, volatile compounds like water, methane and ammonia can freeze into ice. This fundamental temperature gradient is the architect of solar system diversity. Within this turbulent disk, the journey from atom to planet begins with the humblest of interactions. Microscopic dust grains, no larger than smoke particles, gently collide. At first, these collisions are slow, almost tender. Electrostatic forces, the same invisible attraction that makes a balloon stick to your hair, cause these tiny particles to adhere. They stick together, forming larger grains, then pebbles, then small rocks. This process, known as accretion, is the fundamental building block of planets. Imagine billions upon billions of these tiny grains, swirling, colliding, growing. It is a slow, patient accumulation, like snowflakes gathering into a snowball. As these aggregates grow larger, reaching sizes of a few meters or even kilometers, gravity begins to assert its dominance over electrostatic forces. These larger bodies, now called planetesimals, begin to attract each other more strongly. Their collisions become more energetic, yet still often constructive. They merge, growing ever larger, clearing out their orbital paths within the disk. In the inner, hotter regions of the protoplanetary disk, where ices cannot condense, the growing planetesimals are composed primarily of rock and metal. These terrestrial planetesimals continue to collide and merge, gradually forming the solid, rocky cores of what will become planets like Mercury, Venus, Earth, and Mars. Their growth is limited by the available rocky material, resulting in worlds of moderate size and high density, but venture further out, beyond what we call the frost line, the distance from the star where temperatures drop sufficiently for water ice to condense. Here the story changes dramatically. Not only are there silicates and metals, but vast quantities of water ice, methane ice, and ammonia ice are also available. This abundance of solid material allows planetesimals to grow much, much larger, much more quickly. Once a core reaches a critical mass, perhaps 10 times that of Earth, its gravitational pull becomes immense. It begins to rapidly accrete the surrounding hydrogen and helium gas directly from the protoplanetary disk. This runaway accretion is how the gas giants are born. Jupiter, Saturn, Uranus, and Neptune, worlds of colossal size primarily composed of hydrogen and helium, with relatively small, icy, rocky cores. The formation of these gas giants has a profound impact on the entire nascent solar system. Their immense gravity stirs the remaining planetesimals, sending some hurtling into the inner system, others out into the vast cold beyond. They act as cosmic shepherds, shaping the orbits of the smaller inner planets and occasionally ejecting entire worlds from the system. This gravitational dance creates the architecture we observe today, with the rocky worlds nestled close to the star and the gas giants dominating the outer reaches. As the planets grow, their gravitational influence clears out the remaining gas and dust from their orbital paths. The protoplanetary disk, once a thick, opaque veil, gradually dissipates, either accreted by the growing planets, drawn into the central star, or blown away by the stellar wind. This entire process, from the initial collapse of a molecular cloud to the formation of a stable planetary system, can take tens of millions of years, a blink in cosmic time, yet an eternity from our human perspective. Among these emerging worlds, a particularly vital ingredient often makes its presence known: water. While some water might be incorporated directly during a planet's formation, much of it, especially for inner rocky worlds like Earth, is believed to arrive later. During the tumultuous period of heavy bombardment, icy comets and water-rich asteroids, flung inward by the gravitational perturbations of the giant planets, delivered vast quantities of water to the young Earth. These impacts, once seen as purely destructive, were in fact crucial for seeding our world with the very substance essential for life. As the early Earth cooled, this water condensed, forming the first oceans. Its atmosphere, initially a toxic brew, slowly evolved. Volcanic activity released gases, and the presence of liquid water began to shape the surface. The stage was set. The cosmic ingredients, the stardust, the water, the stable orbit around a life-giving star, had all converged. And this, perhaps, is the most profound revelation of our journey. The universe, in its grand, indifferent dance, not only creates stars and elements, but also crafts the delicate conditions for existence. Our solar system, once thought unique, is now understood to be but one of countless others. We've discovered thousands of exoplanets orbiting distant stars, confirming that planet formation is a common, perhaps universal outcome of stellar birth. Each exoplanet detection, each new system revealed, whispers a tantalizing question. How many of these worlds harbor conditions ripe for life? How many have received the necessary ingredients, the stardust and the water, and found themselves in that precious temperate zone around their star, neither too hot nor too cold? The fundamental forces, the atomic ballet, the stellar cycles of birth and death, the patient accretion of dust into worlds, all these seemingly disparate phenomena are interwoven threads in the cosmic tapestry. They lead with astonishing elegance to the possibility of a blue marble suspended in space, teeming with life. We, the observers, the conscious stardust, are the living embodiment of this profound connection, standing at the threshold of understanding not just how the universe works, but how it creates the very stage for our existence. Our journey into the cosmos is, in the deepest sense, a journey into ourselves. The story of planets is the story of homes, and the search for life beyond our own is the universe asking itself, through us, if it is truly alone. We have journeyed through the genesis of stars and the birth of worlds, contemplating the profound alchemy that transforms stardust into planets, and perhaps into life itself. The universe, in its grand design, seems to be reaching out, asking if it is truly alone. Your hand, perhaps, still rests lightly upon a surface, a table, a book, your own knee, feeling the phantom solidity of electromagnetic repulsion, a testament to the forces we have explored. But now, let us lift our gaze from the delicate ballet of atoms and the intricate waltz of planets, and truly begin to understand the stage upon which this cosmic drama unfolds. For the search for life, for understanding our own existence, requires context. It demands that we comprehend the vast, sprawling architecture that houses not just our sun and its small retinue of worlds, but billions upon billions of others. We speak, of course, of galaxies. Imagine, if you will, that you are floating in the quietude of interstellar space, a vast dark canvas stretching in every direction. Before you a breathtaking spiral unfurls, a colossal pinwheel of stars, gas and dust slowly turning in majestic silence. This, our dear audience, is the Milky Way, our galactic home. It is a structure so immense that light travelling at its dizzying speed takes approximately 100,000 years to cross from one edge to the other. Within its luminous embrace reside an estimated 100 to 400 billion stars, each a sun, many with their own planetary systems, all bound together by the relentless grip of gravity. We reside not at its bustling heart, but in a quieter, more tranquil suburb, nestled within one of its sweeping spiral arms, the Orion arm to be precise. Our Sun, a relatively modest star, completes one full orbit around the galactic centre roughly every 220 to 250 million years. Think of the geological epochs that have unfolded on Earth in just one galactic year. Dinosaurs rose and fell, continents drifted, and life evolved from single cells to complex beings, all while our solar system completed a single stately revolution around the galactic core. The Milky Way is a testament to the power of gravity on the grandest scales. Its central bulge, a densely packed region of older stars, glows with a golden light, hinting at the supermassive black hole Sagittarius A that anchors it all. Around this core, the thinner disk of spiral arms teeming with younger, hotter, blue-white stars and vibrant nebulae traces paths of ongoing star formation. And enveloping it all, a diffuse, nearly invisible halo of ancient stars and globular clusters, like scattered pearls, whispers of the galaxy's long history. But the Milky Way, for all its splendour, is merely one island in an unfathomable ocean. As our instruments grew more powerful, our understanding deepened, revealing a universe populated by countless such islands, each a galaxy unto itself. We gaze out now, not just at stars, but at entire cities of stars, stretching farther than our minds can easily grasp. Some galaxies are like ours, elegant spirals, their arms winding gracefully like cosmic staircases. Others are majestic ellipticals, giant cosmic rugby balls, often older, redder, and less active in star formation, their stars moving in more random, less organised orbits. Still others are irregulars, chaotic and beautiful, often the result of gravitational encounters or collisions between their larger neighbours, their forms distorted and vibrant with bursts of new starbirth. These galaxies are not static, isolated entities. They are social creatures, drawn together by the omnipresent force of gravity. They cluster together, forming groups like our own local group, a collection of over 50 galaxies including the Andromeda Galaxy, our majestic neighbour, which is currently hurtling towards us on a collision course. In a few billion years, our two great spirals will merge, a slow-motion cosmic ballet that will sculpt a new, larger elliptical galaxy. Beyond these groups lie even grander structures, galaxy clusters containing hundreds or even thousands of galaxies, bound by their collective gravitational pull. And then the superclusters, vast filaments and sheets of galaxies stretching across millions of light years, interspersed with immense cosmic voids, regions of near emptiness. This is this cosmic web, a breathtaking sponge-like structure that represents the largest known organization of matter in the universe, an intricate tapestry woven by gravity since the earliest epochs. Yet as we mapped these colossal structures, as we meticulously observed the rotation of galaxies and the movement of clusters, a profound puzzle emerged. The visible matter, the stars, the gas, the dust, everything that emits or reflects light simply wasn't enough. It wasn't enough to explain how quickly galaxies spin without flinging themselves apart, or how galaxy clusters remain gravitationally bound. The universe, it seemed, was hiding something. Imagine a grand symphony orchestra playing a magnificent piece. You hear the violins, the brass, the percussion, all the instruments you can see. But the music is richer, fuller, more resonant than these visible instruments alone could produce. There's a deeper, unseen current, a hidden force shaping the melody. This, in essence, is the mystery of dark matter. We hypothesize that a vast amount of unseen, non-luminous, non-baryonic matter permeates the cosmos. It doesn't interact with light, it doesn't absorb, emit, or reflect it. It is entirely transparent to electromagnetic radiation, hence dark, but it interacts gravitationally. It is the invisible scaffolding upon which the cosmic web is built, the unseen hand that guides the formation and evolution of galaxies and clusters. Without dark matter, our universe as we know it simply wouldn't hold together. It accounts for approximately 27% of the total mass energy of the universe, a silent, pervasive architect, shaping the cosmos from the shadows. Its true nature remains one of the most compelling mysteries in astrophysics, a frontier of discovery that promises to reshape our understanding of matter itself. But the universe, in its infinite capacity for surprise, holds yet another, even more enigmatic secret. For centuries we assumed that gravity, being an attractive force, would inevitably slow down the expansion of the universe, perhaps even reverse it, leading to a big crunch. Our observations, however, revealed a startling truth. As we peered deeper into space using distant type Ia supernovae as cosmic standard candles, celestial lighthouses of known intrinsic brightness, we discovered that the expansion of the universe is not slowing down. It is in fact accelerating. The cosmic fabric itself is stretching at an ever-increasing rate, pushing galaxies further and further apart, faster and faster. This profound discovery necessitated the introduction of another mysterious component: dark energy. Imagine the universe as a vast, stretching rubber sheet. You might expect it to sag and slow its stretching due to its own weight. Instead, it's as if the sheet itself has an inherent springiness, an intrinsic property that pushes it outwards, causing it to stretch faster and faster. Dark energy is thought to be an inherent property of space itself, a kind of cosmic anti-gravity that counteracts the attractive force of matter. It accounts for roughly 60% of the total mass energy of the universe, making it the dominant component of our cosmos. It is the force that dictates the ultimate fate of everything, a quiet, inexorable push that will likely determine whether the universe expands forever, growing colder and emptier, or meets a different end. Its nature is even more elusive than dark matter, a true enigma that challenges our deepest understanding of fundamental physics. So, as your consciousness expands to encompass these grand scales, from the delicate dance of electrons to the colossal sway of dark matter, from the gentle hum of hydrogen fusion to the accelerating stretch of dark energy, pause for a moment. Feel the quiet awe that such knowledge evokes. We have journeyed from the subatomic to the supergalactic, grappling with forces both familiar and profoundly alien. understanding that the universe is far stranger, more beautiful and more mysterious than we ever dared to imagine. The search for exoplanets, for life beyond Earth, is a deeply personal quest for humanity. But it is also a quest framed by these cosmic titans, by the galaxies that house stars, by the dark matter that binds them, and by the dark energy that propels them apart. We are but tiny observers on a small world, yet our minds can grasp the immensity, the elegance, and the enduring mysteries of this magnificent cosmos. The journey of astrophysics, we realize, is not just about finding answers, but about cultivating a profound appreciation for the questions themselves, and for the astonishing silent architecture that continues to unfold before us. From the silent dance of dark matter, shaping galaxies with its unseen gravity, to the enigmatic push of dark energy dictating the accelerating fate of the cosmos, the universe presents mysteries that humble and inspire. These profound forces, unseen yet utterly dominant, define the grand architecture within which all visible matter, all light, all life must exist. But as we gaze upon this vast, elegant, and often bewildering tapestry, our minds, quite naturally, drift to a question as ancient as thought itself. Are we alone? The quest for life beyond Earth is not merely a scientific endeavour, it is a primal yearning, an echo of our own existence projected onto the cosmic canvas. It asks not only if life exists elsewhere, but what it might be and how it might thrive amidst the extraordinary diversity of worlds we are now discovering. We begin this quiet journey into astrobiology by first defining what we mean by life in an astrophysical context. While the universe may hold wonders beyond our current comprehension, our search is grounded in what we know, the intricate carbon-based biochemistry that flourishes here on Earth. Carbon, with its remarkable ability to form 4 stable bonds, acts as the universe's master builder, creating the complex molecular chains essential for biological functions. And water, that ubiquitous solvent, provides the medium, the cosmic crucible, in which these complex reactions can occur. Liquid water, therefore, becomes our primary beacon, our guiding star in the search for extraterrestrial biology. Imagine, if you will, a star like our Sun, burning steadily for billions of years. Around it, planets orbit, each tracing its own path through the cosmic dark. For a planet to harbour liquid water on its surface, it must reside within a very specific range of distances from its star, a region we call the circumstellar habitable zone, often affectionately termed the Goldilocks zone. Too close and the water boils away into vapour, lost to the star's scorching heat. Too far and it freezes solid, locked away in icy desolation. Just right and water can flow, pool, and perhaps nurture the spark of life. This habitable zone, however, is not a fixed boundary. It is a dynamic concept shifting with the nature of the star itself. A smaller, cooler star like a red dwarf would have a habitable zone much closer to its fiery heart, where planets might be tidally locked, presenting one face eternally to their star, while the other shivers in perpetual night. A larger, hotter star burning through its fuel more rapidly would push its habitable zone further out, offering less time for life to evolve before its eventual fiery demise. The longevity and stability of the star are paramount, offering billions of years for the slow, meandering dance of evolution to unfold. Yet, merely being in the habitable zone is not enough. A world capable of sustaining life is far more complex than just a watery sphere at the right distance. Your hand rests on a surface, perhaps a desk or a book. Consider the intricate conditions that allowed the atoms within that object, and indeed within your own hand, to coalesce and form something so remarkably ordered. For a planet to truly be a cradle for life, it needs a host of supporting features. First, a big stable atmosphere is crucial. This not only traps heat, preventing extreme temperature fluctuations, but also shields the surface from harmful stellar radiation and micrometeoroid impacts. An atmosphere, often a delicate blend of gases, provides the pressure necessary for liquid water to exist, and its composition can even be a telltale sign of life itself. Then there is the silent, invisible guardian of strong planetary magnetic field. Generated by the churning molten iron core of a world, this magnetic shield deflects the constant barrage of charged particles from its star, the stellar wind, preventing the atmosphere from being stripped away into space over eons. Without it, potentially habitable world could become a barren wasteland, its precious water molecules broken apart and lost to the void. Mars, once believed to have rivers and oceans, stands as a stark reminder of this planetary vulnerability. Consider, too, the slow, majestic dance of plate tectonics on Earth. This geological process, driven by the planet's internal heat, constantly recycles nutrients, regulates atmospheric carbon dioxide levels, a key greenhouse gas, and creates diverse habitats. It is a planetary heartbeat, essential for long-term climate stability and the continuous replenishment of the raw materials life requires. Without this internal dynamism, a world might quickly become geologically inert, its surface weathering away without renewal, its potential for sustained life dwindling. And what of our own Earth's celestial companion, the Moon? Its relatively large size and close proximity stabilize Earth's axial tilt, preventing extreme wobbles that would lead to catastrophic climate shifts. This gravitational anchor ensures the stable seasons and predictable climates that have allowed life to flourish and diversify over geological timescales. A planet without such a stabilizing influence might experience chaotic climatic swings, making the persistent evolution of complex life a far more arduous, if not impossible, endeavor. Finally, we look to the grand protector in our own solar system, Jupiter. This gas giant, with its immense gravitational pull, acts as a cosmic vacuum cleaner, deflecting or absorbing countless comets and asteroids that might otherwise impact the inner planets, including Earth. Without such a planetary guardian, the frequency of devastating impacts could be so high as to prevent the long periods of calm necessary for complex life to emerge and thrive. The intricate balance of a planetary system, it seems, is as crucial as the individual world itself. With these criteria in mind, the search for life shifts from a mere question of distance to a profound exploration of planetary characteristics. Our tools, many of which we have already discussed, become even more vital. Spectroscopy. The art of dissecting light once again takes center stage. By analyzing the light passing through an exoplanet's atmosphere when it transits its star, we can discern the chemical fingerprints of its constituent gases, the presence of certain molecules in unusual abundances, particularly in combination, say, oxygen and methane coexisting in a state of disequilibrium, could be a powerful biosignature, a potential sign of biological activity. Oxygen, a highly reactive gas, would quickly disappear from an atmosphere without constant replenishment, a replenishment often provided by life itself through photosynthesis. Beyond atmospheric composition, future telescopes might even be sensitive enough to detect other, more direct signs. Imagine observing the red edge of chlorophyll on a distant exoplanet, the specific spectral signature of vegetation reflecting infrared light. Or in the realm of truly advanced civilizations, perhaps even techno-signatures. Artificial radio transmissions, laser pulses, or even the grand engineered structures like Dyson spheres, designed to capture a star's entire energy output. These would be unmistakable proclamations of intelligence, echoing across the vastness of space. Yet for all the scientific advancements, for all the thousands of exoplanets discovered, the universe remains profoundly silent to our inquiries. This silence brings us face to face with one of the most compelling and unsettling questions in astrobiology. The Fermi paradox. If the universe is so vast, so ancient, and if the conditions for life are seemingly abundant, then where is everybody? Why haven't we detected any evidence of other advanced civilizations? This paradox, first posed by physicist Enrico Fermi, opens a Pandora's box of possibilities. Perhaps life, while common, rarely progresses to intelligent spacefaring civilizations. This is the idea of a great filter, some insurmountable obstacle that prevents life from making the leap from simple to complex, or from complex to intelligent, or from intelligent to interstellar. This filter could be in our past, making our existence extraordinarily rare, or, more chillingly, in our future, a common fate awaiting all advanced civilizations. Perhaps the rare Earth hypothesis holds true, suggesting that the precise combination of factors needed for complex, enduring life, a stable star, a planet with plate tectonics, a large moon, a gas giant protector, the right chemical composition, and a long, peaceful cosmic epoch is indeed exceptionally rare. Earth, in this view, is not just a habitable world, but a uniquely fortunate one. Or perhaps they are simply too far away, their signals diluted by the immense cosmic distances. Or perhaps they are so profoundly different from us, their forms of communication and existence so alien that we simply fail to recognize them. Or, in a more contemplative vein, perhaps they exist, but choose silence, observing us from afar, adhering to a prime directive of non-interference, allowing nascent civilizations like ours to develop naturally. The very act of asking these questions, of searching, of contemplating our place in this fast accelerating cosmos, is a testament to the life that has flourished here on Earth. It is a journey that connects the subatomic origins of matter, forged in the hearts of stars and scattered by supernovae, to the grand, accelerating architecture of the cosmos, and ultimately to our own profound quest for understanding. We are, after all, made of stardust, imbued with a curiosity that compels us to look beyond our pale blue dot, to wonder, and to continue listening to the silent whispers of the universe, hoping one day for an answer. The search in its quiet reverence continues. We have journeyed far together, haven't we? From the silent, bustling emptiness within a single atom to the profound, echoing silence between galaxies, a vast cosmic tapestry has unfolded before us. We have peered into the hearts of collapsing stars, traced the delicate fingerprints of light across cosmic distances, and wrestled with the profound questions of life's presence and absence across the universe. Our explorations have led us to the most ancient and enduring mysteries, the unseen forces of dark matter and dark energy, and the unsettling quietude of the Fermi paradox. Yet, even as these grand questions linger, a deeper, more fundamental inquiry beckons, drawing us back to the very first moments of existence and forward to the universe's ultimate destiny. Take a moment now, if you will. Let your gaze drift beyond the window, or simply close your eyes and feel the quiet hum of the world around you. Consider the sheer audacity of our journey, to understand not just what is, but how it all began and where it is all going. This is where we turn our gaze to the grandest narrative of all, the story of the universe itself, from its fiery birth to its distant, perhaps silent end. We speak, of course, of the Big Bang, not an explosion in space as we once mistakenly imagined, but an expansion of space itself, a genesis of time, space, and all that is. We have touched upon it before as the primordial soup from which the first hydrogen and helium atoms congealed. But let us now linger there, in that unimaginably dense and hot infancy. For in the lingering echoes of that cosmic dawn, we find some of the most profound evidence of our universe's beginning. Imagine the universe not as a vast empty stage onto which matter was flung, but as an infinitely small, infinitely hot point, pregnant with all potential. From this singularity, space and time began to stretch, cooling as they expanded. Within fractions of a second, the fundamental forces we now observe, the strong and weak nuclear forces, electromagnetism and gravity, differentiated themselves from a unified superforce. Quarks and gluons swam in a plasma so dense, so energetic, that matter as we know it could not yet coalesce. As the universe continued its breathtaking expansion and cooling, a critical threshold was crossed. After about 380,000 years, the temperature dropped sufficiently for electrons to combine with atomic nuclei, primarily hydrogen and helium, to form the first stable atoms. This event, known as recombination, had a profound consequence. It made the universe transparent. Before this, photons were constantly scattering off free electrons and protons trapped in a cosmic fog. Once the electrons were bound to atoms, these photons were free to stream across the cosmos. These liberated photons, stretched and cooled by billions of years of cosmic expansion, are what we detect today as the cosmic microwave background, or CMB. It is the faint, uniform glow that permeates all of space, a pervasive whisper of the early universe. Your television, if you have ever tuned it to an analog channel, receives a tiny fraction of this ancient light as static. It is the oldest light we can ever hope to see, a perfect blackbody spectrum, uniform to an astonishing degree, yet with tiny fluctuations, the seeds from which all future galaxies and structures would grow. The CMB is not merely evidence, it is a direct photograph of the universe when it was just a baby, a silent, powerful testament to the Big Bang. Further corroborating this grand origin story is the observed abundance of the lightest elements. In the first few minutes after the Big Bang, when the universe was still hot enough for nuclear reactions but cool enough for stable nuclei to form, a process known as Big Bang nucleosynthesis occurred. Protons and neutrons fused to create deuterium, helium-3, helium-4, and tiny traces of lithium. The precise ratios of these elements observed in the oldest, most pristine parts of the universe perfectly match the predictions of the Big Bang model. This cosmic recipe, cooked in the universe's infancy, provides another indelible fingerprint of creation, confirming our understanding of those earliest, most energetic moments. So we stand on firm ground in understanding our beginnings. But what of our end? Where is this accelerating universe driven by the mysterious dark energy ultimately headed? For centuries, humanity has pondered the ultimate fate of all things, from the individual to the entire cosmos. Science now offers several compelling, if sometimes unsettling, scenarios. The primary factor dictating the universe's ultimate fate is the delicate balance between the outward push of dark energy and the inward pull of gravity. Current observations, particularly the accelerating expansion we discussed, strongly favour a future dominated by dark energy, leading to a scenario often called the Big Freeze or heat death. In this quiet, inexorable future, the expansion of space continues to accelerate, pushing galaxies further and further apart, eventually beyond the reach of our observational horizon. Distant galaxies will recede so quickly that their light will never reach us, rendering them invisible. Our own local group of galaxies might remain gravitationally bound, but even within this small island, stars will eventually exhaust their fuel. Red dwarfs, the longest-lived stars, will burn for trillions of years, but even they will eventually fade. Stellar remnants, white dwarfs, neutron stars and black holes will populate an increasingly dark and empty cosmos. Over truly staggering timescales, even these remnants will succumb to the relentless march of entropy. White dwarfs will cool into black dwarfs. Neutron stars will remain stable, but their light will be long extinguished. Black holes, those cosmic titans, will slowly evaporate through a process called Hawking radiation, a quantum whisper across billions upon billions of years, until even they vanish into nothingness. Eventually, the universe will become a cold, dark, incredibly dilute expanse of photons and fundamental particles, too far apart to interact, a state of ultimate equilibrium and maximum entropy, a universe that has simply run out of energy to do anything. A quiet, eternal silence. Other scenarios, though less likely given present data, remind us of the universe's profound possibilities. If dark energy were to strengthen dramatically, a big rip might occur, where the expansion becomes so violent that it eventually tears apart galaxies, stars, planets, and even atoms themselves, literally ripping the fabric of space-time. Conversely, if dark energy were to weaken or reverse its effect, gravity might eventually win, halting the expansion and pulling all matter back together in a big crunch, collapsing the universe back into an incredibly dense, hot state, perhaps even a new singularity, potentially leading to a cyclical universe. But for now, the data points towards a slow, cold, quiet fade. It is a humbling thought, isn't it? That the vibrant, dynamic universe we observe, teeming with life and light, might ultimately drift into such a profound stillness. Yet even in contemplating such a distant future, we are struck by another astonishing facet of our cosmos, its remarkable fine-tuning. Consider the fundamental constants of nature, the strength of the strong nuclear force, the electromagnetic force, the gravitational constant, the mass of an electron, the speed of light. These are not arbitrary numbers. They are the bedrock upon which our universe is built, the dials set at the moment of creation that dictate everything from the stability of atoms to the formation of galaxies. If the strong nuclear force were even slightly weaker, atomic nuclei wouldn't hold together, and no elements heavier than hydrogen could form. If it were slightly stronger, hydrogen would burn too quickly and stars would be short-lived. If the electromagnetic force were marginally different, atoms might not form stable bonds, or stars might not ignite. If gravity were a touch stronger, the universe might have collapsed back on itself long ago, a touch weaker, and galaxies would never have formed. It is as if the universe's fundamental parameters are exquisitely balanced, a cosmic symphony played with astonishing precision, allowing for the emergence of complexity, stars, planets, and ultimately life. This observation, often termed the fine-tuning problem, is one of the most profound mysteries facing physicists and cosmologists. Is it merely a colossal coincidence? Are there other universes with different constants, a multiverse, where we simply happen to reside in the one hospitable to life? Or is there a deeper, as yet undiscovered principle that dictates these values? We do not yet have the answers, but the question itself underscores the astonishing elegance and apparent deliberate design woven into the fabric of reality. As we conclude this chapter, and indeed our journey through the fundamentals of astrophysics, we are left not with a neat package of all answers, but with an expanded sense of wonder and a renewed appreciation for the vastness of the unknown. We have pushed the boundaries of human understanding from the quantum foam of the vacuum to the edge of the observable universe, tracing the story of cosmic evolution with remarkable clarity. Yet, every solved mystery unveils a dozen new ones. We grapple still with the nature of dark matter and dark energy, the origin of the Big Bang itself, the unification of quantum mechanics and general relativity, and the ultimate meaning of the fine-tuned universe. This is the enduring beauty of science, isn't it? It is not a destination, but a continuous journey, a persistent, quiet curiosity that drives us to look ever deeper, ever further. We, the inhabitants of this pale blue dot, are granted the extraordinary privilege of observing, questioning, and slowly, patiently unraveling the universe's most profound secrets. Our consciousness, a fleeting spark in the cosmic timescale, allows the universe to reflect upon itself, to ask its own questions. So as we bring our shared adventure to a gentle close, remember the profound interconnectedness of all things. The atoms in your hand were forged in the hearts of ancient stars. The light that warms your face has travelled billions of years to reach you. You are quite literally stardust, a conscious part of this grand, unfolding cosmic drama. Continue to look up, continue to wonder, continue to question. For in that quiet, persistent seeking, we find not only knowledge but a deeper, more profound connection to the astonishing, beautiful, and endlessly mysterious universe we call home. The journey for each of us continues. We have journeyed through the cosmos, tracing the universe from its fiery birth to its inevitable chilling end. We've witnessed the alchemy of stars, the delicate dance of planets, and the persistent whisper of life's potential across the vast expanse. Yet, as our gaze turns towards the horizon of human understanding, we find not a clear vista, but profound shadows, vast and enigmatic, that challenge the very foundations of our knowledge. You are settled, perhaps, with the quiet hum of your own thoughts, the distant sounds of your world, a gentle counterpoint to the cosmic symphony we explore. Take a moment to breathe, to let the immensity of what we've discussed settle into the quiet chambers of your mind. For now we gently lift the veil on the universe's deepest, most perplexing secrets. These are the mysteries that speak not of what we understand, but of what we are only just beginning to grasp, the silent architects of a reality far stranger than we ever imagined. We begin with a whisper of gravity, the force that binds galaxies and shapes the cosmic web. For decades, our calculations of galactic rotation presented a peculiar anomaly. Imagine a cosmic carousel, a galaxy spinning majestically in space. Based on the visible stars, gas and dust, the luminous matter we can detect, the outer edges of this carousel should be slowing down, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. But when we observe galaxies, we find something astonishing. The outer regions are spinning far too quickly, as if held by an invisible hand, a gravitational embrace from something we cannot see. This discrepancy, first rigorously observed by the pioneering astronomer Vera Rubin, was a profound challenge to our understanding. It led us to an inescapable conclusion. There must be a vast amount of unseen matter, a phantom presence exerting gravitational influence without emitting, absorbing or reflecting light. We call this elusive substance dark matter. It is the silent gravitational scaffolding upon which the visible universe is built. Consider its properties. Dark matter does not interact with light, nor does it engage with the electromagnetic force. This means it doesn't form atoms, doesn't coalesce into stars or planets, and doesn't participate in the vibrant chemistry that defines our everyday world. It simply is. It flows through us, through the Earth, through the Sun, almost entirely unimpeded, a ghostly current in the ocean of space. We infer its presence not just from galaxy rotation curves, but from the way it bends light from distant objects through gravitational lensing, creating distorted arcs and multiple images of faraway galaxies. We see its imprint in the growth of cosmic structures, guiding the formation of galaxies and clusters from the earliest epochs of the universe. What is it made of? This remains one of the most compelling questions in all of science. We know it's not ordinary baryonic matter, the protons, neutrons, and electrons that compose everything we've ever touched or seen. Current theories lean towards exotic, as yet undiscovered subatomic particles, perhaps weakly interacting massive particles, or WIMPs. Particles that would interact with normal matter only through gravity and the weak nuclear force. Billions of these particles, if they exist, might be streaming through you right now, utterly undetectable by your senses, a profound testament to the universe's hidden complexity. Dark matter accounts for roughly 27% of the total mass energy of the cosmos, a significant portion of reality that remains shrouded in mystery, a constant reminder of the limits of our current perception. But the universe holds an even deeper secret, one that utterly reshaped our understanding of its ultimate fate. Recall our discussion of the universe's expansion. For decades we assumed that gravity, the dominant force on cosmic scales, would inevitably slow this expansion over time, perhaps even reversing it in a big crunch. Then, in the late 90s, observations of distant Type Ia supernovae, those brilliant, reliable cosmic lighthouses, revealed an astonishing truth. The expansion of the universe is not slowing down, it is accelerating. This discovery was nothing short of revolutionary, earning the Nobel Prize for the astronomers who uncovered it. To explain an accelerating expansion, we must invoke an entirely new, even more enigmatic component of the cosmos: dark energy. This is not a particle, nor a conventional force as we understand it. Instead, dark energy appears to be an inherent property of space itself, a kind of pervasive, repulsive pressure that pushes galaxies apart at an ever-increasing rate. It acts like an anti-gravity, a silent, relentless driver of cosmic dispersion. Dark energy is even more mysterious than dark matter. While dark matter clusters with galaxies, dark energy appears to be smoothly distributed throughout space, its density remaining constant even as the universe expands. It is the dominant component of our universe, comprising an astonishing 60% of its total mass energy budget. We are living in a universe largely governed by two unseen, unknown entities. The visible, tangible universe, the stars, planets, and galaxies, makes up less than 5% of everything that exists. This profound realization leaves us in a state of humble wonder. Our understanding, though vast, is built upon a foundation of fundamental unknowns. What is dark matter? What is dark energy? These questions are not mere scientific puzzles. They are invitations to rethink our place in a universe so much grander and more peculiar than our senses can ever directly perceive. And what of life, that improbable spark of consciousness that allows us to ponder these very mysteries? Our search for extraterrestrial intelligence, while fueled by optimism, is shadowed by another profound enigma, the Fermi paradox. If the universe is so vast, so ancient, and if life is a common cosmic occurrence, as suggested by the sheer number of stars and exoplanets, then where is everybody? Why have we not yet detected any definitive signs of other advanced civilizations? The silence is deafening, inviting a multitude of explanations, each more thought-provoking than the last. Could there be a great filter? A formidable obstacle that prevents life from progressing to an interstellar detectable stage? This filter could lie in our past, suggesting that the emergence of life itself, or the leap from simple to complex life, or the development of intelligence, is extraordinarily rare. Perhaps the conditions on Earth were uniquely favourable. A rare Earth hypothesis where a confluence of factors, a stable star, a large moon, plate tectonics, a gas giant protector, the right atmospheric composition, liquid water, and a precise orbital distance, all aligned in an almost impossibly improbable manner. Or perhaps the great filter lies in our future. Could advanced civilizations inevitably destroy themselves through technological hubris, environmental collapse, or internecine conflict? Are we, humanity, hurtling towards our own such filter, our ability to harness immense power outstripping our wisdom to wield it? This is a sobering thought, a cosmic warning echoing across the void. Other possibilities abound. Perhaps advanced civilizations are so far beyond our current comprehension that we simply don't recognize their signals, or they communicate in ways we cannot yet conceive. They might have transcended physical forms, existing as pure energy or information, rendering them invisible to our radio telescopes. Or perhaps the distances are simply too vast, the cosmic ocean too wide for any civilization to bridge the gaps before their star fades or their planet becomes uninhabitable. The Fermi paradox forces us to confront not just the question of alien life, but the fragility and preciousness of our own existence. And finally we arrive at the most profound contemplation, one that weaves through all these mysteries, the fine-tuning problem. As we explore the fundamental constants of the universe, the strength of gravity, the electromagnetic force, the weak and strong nuclear forces, the mass of the electron, the very value of the cosmological constant that governs dark energy, we find an astonishing precision. Alter any of these values by even a tiny fraction, and the universe as we know it would not exist. Stars would not form, atoms would not be stable, carbon-based life would be impossible. It's as if the cosmic dial was set with exquisite care, a Goldilocks universe where everything is just right for life to emerge. Is this pure blind chance? An incredible cosmic coincidence that we happen to inhabit the one universe out of countless possibilities where life can exist. This leads to the intriguing yet untestable concept of a multiverse, an infinite ensemble of universes, each with slightly different physical laws and constants. In such a scenario, our universe is merely one among many, and it's no surprise that we find ourselves in one hospitable to life, for we couldn't exist elsewhere. Or does this fine-tuning hint at a deeper underlying principle, a unifying theory that dictates these constants are not arbitrary, but emerge from a more fundamental reality? Perhaps our understanding of physics is incomplete, and what seems like fine-tuning is simply a consequence of a more elegant, all-encompassing framework we have yet to discover. This quest for a theory of everything, a unification of quantum mechanics and general relativity, is the holy grail of modern physics, a profound aspiration to reveal the universe's ultimate blueprint. These are the frontiers of our knowledge, the grandest questions that beckon us forward. Dark matter, dark energy, the silence of the cosmos, the exquisite balance of our physical laws, they are not failures of science, but rather testament to its enduring power to uncover ever deeper layers of reality. They invite us to embrace humility, to marvel at the sheer audacity of existence, and to recognize that our journey of understanding is far from over. You, the conscious observer, are a product of this astonishingly elegant and mysterious universe, a creature of stardust capable of contemplating its own origins and destiny. The Dreamy Academy believes that in these peaceful explorations, in the quiet pursuit of answers to the biggest questions, we find not only knowledge, but a profound connection to the silent architecture of the cosmos, and perhaps to something within ourselves that yearns for understanding. The journey continues always into the beautiful unknown. We have journeyed through the cosmic tapestry, tracing the threads from the infinitesimally small to the impossibly vast, from the fleeting flicker of a proton to the slow, majestic waltz of galaxies. We've unravelled the elegant dance of forces, witnessed the birth and death of stars, and pondered the silent, accelerating expansion of space itself. Our last quiet contemplation brought us to the precipice of a most profound paradox. The universe, in its very architecture, seems almost impossibly tailored for our existence. Your hand rests, perhaps, on a smooth surface, a cool glass, or the warmth of a mug. Consider the fundamental constants that govern the reality beneath your fingertips, the forces that hold the atoms of that surface together, that allow light to reflect into your eyes, that permit the very neural impulses sparking in your brain. These are not arbitrary numbers. They are the bedrock upon which all complexity, all life, all consciousness is built. And as we've quietly mused, if even one of these constants were infinitesimally different, the strength of gravity, the charge of an electron, the mass of a proton, the universe as we know it, with its stars, its planets, its intricate chemistry, would simply not exist. There would be no you, no us, no Dreamy Academy, no quiet moment of reflection. This astonishing precision, this cosmic fine-tuning, leaves us with questions that ripple through the deepest chambers of scientific and philosophical thought. Is it merely an extraordinary coincidence, a lucky roll of the cosmic dice? Or does it hint at something more, something grander, perhaps even beyond our current comprehension? One avenue of thought, often whispered in the hushed halls of cosmology, is the anthropic principle. Do not let the name intimidate you. It is less a scientific theory and more a framework for understanding our unique observational position within the vastness. It asks us to consider the role of the observer, you, us, in shaping what we perceive. The weak anthropic principle offers a deceptively simple yet profoundly humbling perspective. It suggests that we can only observe a universe that is capable of supporting conscious life, because if it weren't, we wouldn't be here to observe it. Imagine a boundless ocean of universes, a cosmic multiverse, each with its own unique set of physical laws and constants, its own particular blend of forces and particles. In this grand, sprawling ensemble, most universes would be sterile, cold, or too hot, collapsing too quickly or expanding too rapidly, utterly devoid of the conditions necessary for stars to form, for carbon to synthesize, for water to condense, for life to stir. But somewhere, amidst this infinite statistical landscape, there would inevitably be a universe, perhaps even many, whose constants just happen to align perfectly. And it is in one such universe, precisely because it permits our existence, that we find ourselves. This perspective doesn't explain why. The constants are what they are in our universe, but it gracefully explains why we observe them to be so. It shifts the question from a search for a unique explanation for our universe's fine-tuning to an acceptance of statistical probability within a vaster cosmic reality. Your hand resting now is a testament not to a singular improbable stroke of luck, but to the sheer overwhelming abundance of cosmic possibilities. We are simply in the universe that allows us to be. But then there is the more daring, more speculative, strong anthropic principle. This posits that the universe must possess properties that allow for the development of life at some stage in its history. This idea ventures into the territory that challenges our conventional scientific frameworks, flirting with concepts of purpose or inevitability. Does the universe, in some fundamental way, require consciousness? Is our existence not merely a fortunate outcome, but an intrinsic part of the cosmic design, perhaps even a condition for its very unfolding? Here, the lines between physics and metaphysics begin to blur, and our quiet curiosity invites us to ponder the deepest implications of our own awareness. These principles, whether weak or strong, are not definitive answers, but rather lenses through which we can gaze upon the cosmic enigma. They remind us that our perspective is inherently limited by our existence, yet simultaneously empowered by our capacity for inquiry. The universe, in its silent majestic indifference, has nonetheless given rise to minds capable of contemplating its own origins and destiny. This in itself is an astonishing elegance, an ordinary miracle unfolding with every thought. As we stand at the threshold of these profound questions, we recognize the inherent humility of scientific exploration. For every answer we uncover, new questions blossom, pushing the boundaries of our understanding further into the unknown. The universe does not yield its secrets easily, nor does it reveal them all at once. It is a slow, thoughtful adventure, a continuous unveiling. Consider the very nature of scientific laws themselves. Are they immutable truths etched into the fabric of reality from the moment of the Big Bang? Or are they emergent properties, patterns that coalesce from a deeper, more fundamental substrate? This question leads us to the grandest quest in modern physics, the search for a theory of everything. Imagine a single elegant framework, a unified tapestry of understanding that could weave together the disparate threads of gravity, electromagnetism, and the nuclear forces. Such a theory, often envisioned as a quantum theory of gravity, would reconcile the smooth, predictable dance of planets with the whimsical, probabilistic flutter of subatomic particles. It would reveal the ultimate architecture of reality, perhaps even shedding light on why the fundamental constants are precisely what they are. Concepts like string theory or loop quantum gravity whisper promises of such unification, proposing that the universe at its most fundamental level is not made of point-like particles but of tiny vibrating strings or discrete loops of space-time. These vibrations, like musical notes on a cosmic instrument, would give rise to all the particles and forces we observe, explaining the symphony of reality from a single harmonious score. While these remain speculative frontiers, they represent humanity's relentless drive to find order, to understand the underlying simplicity that might govern the apparent complexity. Your quiet journey with us through the fundamentals of astrophysics has been an invitation to marvel not just at what we know, but at the vast ocean of what remains to be discovered. The unresolved mysteries, the true nature of dark matter and dark energy, the complete resolution of the Fermi paradox, the ultimate explanation for fine-tuning and the elusive theory of everything, are not gaps in our knowledge to be lamented, but rather luminous beacons guiding the next generation of explorers. They are the fertile ground for new insights, new paradigms, new revolutions in thought. The universe, remember, is not a static painting but a dynamic unfolding drama, And you, with your capacity for wonder and your quiet curiosity, are not merely an audience member, but a conscious, integral part of this grand cosmic play. You are made of the same stardust that birthed the galaxies, animated by the same fundamental forces that sculpt the cosmos. Your thoughts, your questions, your very presence are echoes of existence, ripples in the fabric of space-time, connecting you to the deepest mysteries and the most profound beauties of the universe. As we gently draw this particular exploration to a close, let us carry forward not just facts and figures, but a renewed sense of awe, a heightened appreciation for the intricate dance of reality, and an enduring quiet curiosity. The universe continues its silent, majestic journey, and so too does our quest to understand it. The stars still beckon, the void still whispers, and the journey of discovery for us all has only just begun. The quiet wonder, once awakened, continues to resonate long after the final words are spoken.